This is the second video for section 5.4, and in it we're going to take a look at our second type of comparison test. It's called the limit comparison test, and we're going to consider another example here. So we have the sum of 1 over 3 to the n minus n, and hopefully you're getting better at picking things to compare with. Just looking at 1 over 3 to the n minus n, we can see, oh, well, if we got rid of that minus n, that looks like 1 over 3 to the n, and this is the same as 1/3 to the n, which is geometric, right? We could say the sum of 1 over 3 to the n is that series is a convergent geometric series. Now, the question is, can we use our regular comparison test? Well, if we did what we did in the last video, the denominator of our terms on the left is smaller. So we're dividing by a smaller number, which means the terms on the left are going to be bigger than the terms on the right. Well, we're now greater than a convergent series. Can we be greater? No, we have to be less than a convergent series. So the regular comparison test does not work. The comparison test will not work. In other words, this inequality here, this inequality, the greater than, it goes the wrong way. In order to use the comparison test, that needs to be a less than. So we need a new tool, and that's where the limit comparison test comes in. So with the limit comparison test, we still use our two series, or we still, we're going to use the one that we have, and then we're going to compare that to something that we know. And really, so this has three parts. The one I almost always use, though, is just that first one. So what you do is you take a ratio of a sub n over b sub n. You just divide them. And as long as you get some, and you take the limit of that as n approaches infinity, and as long as you get some limit that isn't 0, then either both series converge or both series diverge. So according to that, that says if we use this comparison test, because the 1 over 3 to the n is a convergent geometric series, as long as we get some constant that's not equal to 0, then the other series will also converge. Let's see how this works. So this says that we're going to take the limit as n approaches infinity of the ratio of our two series. The one that we're comparing to, 1 over 3 to the n, divided by our original 1 over 3 to the n minus n. And it's not really helpful in that form. So we have the limit as n approaches infinity. It's easier to think about this as, instead of dividing, as multiplying by the reciprocal. So we have 3 to the n minus n over 1, which can be rewritten, of course, as 3 to the n minus n over 3 to the n. Well, that's really two separate problems, right? We can split that fraction. This is something we do quite often. So we have 3 to the n over 3 to the n minus n over 3 to the n. And of course that can be simplified because we have the limit as n approaches infinity. 3 to the n over 3 to the n is 1. And then we have minus n over 3 to the n. And the limit doesn't really have any effect on the 1, but the second one, we have infinity over infinity, right? We have n, as n approaches infinity, that's going to go to infinity, and 3 to infinity is also approaching infinity, so we can use L'Hopital's rule here. And so when we use L'Hopital's rule, we get 1 minus the limit. The limit of 1 is just 1. But the second one we're going to apply L'Hopital's rule to, and we get 1 over 3 to the n times the natural log of 3. That's the derivative of 3 to the n. The derivative, write this on the side here, the side. The derivative of 3 to the x is equal to 3 to the x times the natural log of 3. So now when you take that limit as n approaches infinity, you basically get 1 minus 1 over infinity. 1 minus 1 over infinity, which is 0, so this comes out to 1. And that is a constant. Remember what our goal was here with the limit comparison test. We wanted to get some constant L which wasn't equal to 0. So this is not equal to 0. So we can now make our statement. Remember it says, as long as we get some limit that's not equal to 0, then either both series converge or both series diverge. Well, the series we were comparing to converged. So we can say, since 1 over 3 to the n is a convergent geometric series, then the other one, n equals 0, and that started at 0, so I'm going to say 0 to infinity. Then the other one, we have 1 over 3 to the n minus n must also converge by which test? By the limit comparison test. And that's how you do it. So the other example is very similar. Example B. I'm going to go ahead and post the solution for example B. And that's going to do it for section 5.4. And just remember, if it doesn't work out with the regular comparison test, if your inequality doesn't work right, where it has to be greater than a divergent series or less than a convergent series, if that comparison, the inequality doesn't work out, just use the limit comparison test. All right, thank you.